Hello there, and welcome to Cosmic Slumber. Tonight we are drifting into the slow, silent world of dying stars. They swell into giants larger than entire solar systems. They collapse into points smaller than a city. They scatter their bodies across the dark in clouds of glowing dust, and from that scattered dust, new stars, new planets, and new life eventually rise. Some fade so gently it takes billions of years to notice. Some end in a single blinding instant seen across half a galaxy. Some leave behind objects so strange that a teaspoon of them would outweigh a mountain. The more closely we look, the more this ending stops looking like an ending at all. It starts to look like part of a very long, very quiet cycle. If you enjoy these gentle journeys, I invite you to like, subscribe, or leave a thought below. It helps other sleepy minds find their way here, too, one quiet universe at a time. But for now, all you need to do is relax. Let your shoulders soften. Let your eyes grow heavy. Let your thoughts drift outward, past the ceiling, past the clouds, into the space where stars are quietly, patiently coming to an end. Let's begin. Every star that has ever shone is already dying the moment it is born. That sounds harsh until you understand the trade a star makes at birth. A star exists because it is burning fuel faster than gravity can crush it. From its very first flicker of fusion, it is spending a reserve that cannot be refilled. The star does not know this as urgency. It simply glows, layer upon layer, for as long as the balance holds. Eventually, always, the fuel changes character, the balance tips, and the long, unstoppable process of dying begins. A star's entire life, however brilliant, is really just a very slow exhale, spent gradually across billions of quiet years. The sun will not explode. It will simply swell. Many people picture stellar death as fire and violence, but our own star's ending will be closer to a slow stretching. In roughly 5 billion years, the sun will exhaust the hydrogen at its core and begin fusing hydrogen in a shell around it instead. That shift will cause the outer layers to expand enormously, turning the sun into a red giant vast enough to swallow Mercury, then Venus, and quite possibly the orbit where Earth once circled peacefully. There will be no explosion, only a slow, glowing engulfment, spread across a very long stretch of time. A dying star can grow larger than the orbit of Mars. When a sun-like star becomes a red giant, its outer atmosphere puffs outward to a staggering scale. The core shrinks and heats while the outer shell balloons into a diffuse, cooler envelope that can stretch far beyond where its rocky planets once orbited safely. Seen from a distance, such a star would look enormous and strangely dim for its size, its light spread thin across an atmosphere hundreds of times wider than before. It is a strange kind of dying, expanding outward rather than caving inward, even while the true collapse is already beginning deep within. Some stars flicker violently just before settling into old age. As a star nears the end of its hydrogen-burning life, its internal balance can grow unstable. In stars like the Sun, a sudden ignition of helium in the core, sometimes called a helium flash, can release an intense pulse of energy in a matter of seconds, even though the star's outward brightness barely changes. It is an entirely hidden event, a violent internal shudder wrapped in a calm exterior. The star does not announce this moment to the universe. It simply steadies afterward, having quietly crossed into the next stage of its long decline. A dying star can shed its outer layers like a slow exhale of glowing gas. Once a sun-like star has swollen into a red giant and burned through its usable fuel, it begins to lose its grip on its own atmosphere. Stellar winds carry the outer layers away in vast shells of gas and dust, drifting outward over thousands of years. What remains behind is a small, hot, exposed core, no longer hidden beneath the layers it once wore. The lost material does not vanish. It spreads into space, lit from within by the star it used to surround. Planetary nebulae have nothing to do with planets. The name is one of astronomy's odder accidents. Early observers looking through primitive telescopes saw glowing, rounded shells of gas around dying stars and thought they resembled the pale disks of planets. The name stuck, even though these objects are the expelled outer layers of a star in its final act, not planets at all. Each one is a farewell portrait, gas and dust lit by the small hot core left behind, glowing for a few tens of thousands of years before fading into the surrounding dark. What is left after a star sheds its atmosphere is called a white dwarf. This is the calm, quiet ending most stars reach. A white dwarf is the exposed core of a star like the Sun, no longer fusing fuel, held up only by the strange pressure of tightly packed electrons refusing to be crushed any further. It is roughly the size of Earth, yet it carries the mass of a star. It no longer produces new energy. It only glows from stored heat, slowly, patiently, for an unimaginably long time. A white dwarf can pack the mass of the Sun into a sphere the size of Earth. That density is almost impossible to picture using ordinary experience. A teaspoon of white dwarf material would weigh several tons, heavier than a car, heavier than a small house, compressed into a space that could sit in your palm. The atoms inside are no longer arranged the way they are in ordinary matter. They have been crushed into a strange, dense state where familiar rules of space and structure begin to bend under gravity's patient, relentless pressure. White dwarfs are held up by a rule of quantum physics, not by fusion. Ordinary stars balance gravity with the outward push of nuclear fusion. A white dwarf has no fusion left to offer. Instead, it survives by something called electron degeneracy pressure, a quantum mechanical rule that prevents electrons from being squeezed into the same space and state as one another. That's strange. Invisible resistance is the only thing standing between the white dwarf and total collapse. It is one of the more startling truths in astrophysics that some dead stars are held together by rules borrowed from the smallest particles imaginable. There is a mass limit beyond which a white dwarf cannot exist. Called the Chandrasekhar limit, it sits at about 1.5 times the mass of the Sun below that threshold. Electron degeneracy pressure can hold a dead star's core together indefinitely. Above it, that pressure fails, and the core cannot resist gravity any longer. This single number quietly decides the fate of countless stars across the galaxy, marking the line between a slow, cooling ending and something far more violent and sudden. A white dwarf that crosses that limit can detonate entirely. If a white dwarf gains extra mass, perhaps by pulling material from a companion star, it can be pushed past the Chandrasekhar limit. What follows is not a gradual collapse but a runaway thermonuclear explosion that consumes the star in a matter of seconds. This is called a Type Ia supernova, and because it always seems to happen at almost exactly the same mass, these explosions shine with a remarkably consistent brightness, letting astronomers use them as reliable distance markers across the universe. Some dying stars steal mass from a neighboring star before they explode. In binary systems, stars are often close enough that one can pull material from the other through gravity. A white dwarf orbiting close to a swelling companion may siphon off gas, slowly gaining mass it was never born with. This quiet theft can continue for a long time, until the day the white dwarf finally crosses its limit and detonates, ending not only its own story but rewriting the fate of the star that unknowingly fed it. Massive stars die in a completely different, far more violent way. A star many times heavier than the Sun does not fade gently into a white dwarf. Instead, it fuses heavier and heavier elements in its core, layer by layer, like an onion of increasingly extreme chemistry, until it reaches iron. Iron is the point where fusion stops paying off. No further fusion can release energy from it. Within moments of forming an iron core, such a star loses its internal support entirely and begins one of the fastest, most catastrophic collapses in nature. Massive stars build an onion of elements in their final days. In the last stages of a massive star's life, its interior becomes layered like the inside of a planet, hydrogen on the outside, then helium, then carbon, oxygen, neon, silicon, and finally a core of iron at the center. Each layer represents a different fuel being burned in sequence, faster and faster as the star races toward its end. What took millions of years for hydrogen can take mere days for silicon, a sign that the star's final chapter arrives far more quickly than everything before it. The core of a dying massive star can collapse in under a second. Once an iron core stops producing outward energy, gravity takes over almost instantly. The core, which may be about the size of Earth, can collapse down to a sphere only a few dozen kilometers across in a fraction of a second. It is one of the fastest transformations of matter known to science, an entire stellar core folding inward faster than a human eye could ever register the change, all in complete and total silence. A supernova sends out a wave of neutrinos before it sends out light. When a massive star's core collapses, an enormous burst of nearly massless particles called neutrinos escapes almost instantly, passing through the star's outer layers as though they were not even there. The visible explosion, the burst of light we associate with a supernova, actually takes hours to catch up, because light has to fight its way through the star's dense material first. In effect, a supernova announces itself invisibly long before it ever announces itself to the eye. In 1987, scientists detected a supernova's neutrinos hours before they saw its light. A star known as Sangelik, in a nearby galaxy, ended its life in an event now called SN 1987A. Detectors deep underground picked up a brief pulse of neutrinos passing through the Earth itself, registering for only a matter of seconds. Hours later, telescopes around the world caught the visible flash. It remains one of the clearest confirmations that a dying star speaks first in a language almost nothing can block, and only afterward in the language of light. Neutrinos from a dying star can pass through you without you ever noticing. Trillions of neutrinos from distant stars, and from our own sun, pass through your body every single second, day and night, whether you are awake or asleep. They rarely interact with ordinary matter at all. During a supernova, that quiet flood becomes a flood many times larger, an invisible storm of particles rushing outward and straight through planets, moons, and people alike, leaving barely a trace of its passing. A star's core can bounce like a compressed spring during collapse. As the collapsing core of a massive star reaches extreme density, the same quantum pressure that supports white dwarfs briefly resists the crush, causing the core to rebound outward in what is sometimes called a core bounce. That rebound sends a shockwave slamming into the still-falling outer layers of the star. It is one of the pieces of the puzzle that helps turn a silent collapse into the visible explosion astronomers eventually witness from far away. Supernovae can outshine an entire galaxy for a few weeks. During its peak, a single exploding star can release as much light as billions of ordinary stars combined, briefly rivaling the total brightness of the galaxy that contains it. From across unimaginable distances, that single point of light can appear to equal an entire swirling city of stars. Then, over weeks and months, it slowly fades, leaving behind a fainter object and a debris field expanding outward into the surrounding dark. What remains after a massive star explodes can be a neutron star. If the collapsing core is not massive enough to become a black hole, it can settle into an object called a neutron star, made almost entirely of tightly packed neutrons. It typically measures only about 20 kilometers across, yet contains more mass than the Sun. It is one of the densest objects that can exist without collapsing entirely into a singularity, a small, quiet remnant hiding an almost unbelievable amount of compressed material. A neutron star packs the mass of the Sun into a city-sized sphere. If you could stand on its surface, gravity would be so extreme that an object dropped from shoulder height would strike the ground within a fraction of a second, moving at a significant portion of the speed of light. A sugar cube-sized piece of neutron star material would weigh roughly as much as a mountain here on Earth. It is difficult to hold that density in your mind for long without the comparison starting to feel unreal. Some neutron stars spin hundreds of times every second. When a star's core collapses into a neutron star, it conserves its rotation the way a spinning skater speeds up by pulling their arms in. A slowly rotating star can end up spinning many times per second, once compressed down to city-scale size. Some neutron stars, known as pulsars, spin so quickly and so precisely that their timing rivals the steadiness of atomic clocks, ticking away in the dark long after the star that made them has gone silent in every other way. Pulsars appear to blink because of a beam, not a heartbeat. A pulsar is a rapidly spinning neutron star with intense beams of radiation streaming from its magnetic poles. If one of those beams happens to sweep across Earth as the star rotates, we detect a regular pulse of radiation, much like a lighthouse beam sweeping past a ship at sea. The star is not actually flashing. It is simply spinning steadily while its beam occasionally points our way, tracing an ancient, silent rotation across the dark. Some dead stars carry magnetic fields trillions of times stronger than Earth's. These are called magnetars, a rare and extreme kind of neutron star with magnetic fields so powerful they could theoretically distort atoms from thousands of kilometers away. Their surfaces occasionally shift in sudden ruptures called starquakes, releasing bursts of radiation intense enough to briefly outshine everything else in the sky at certain wavelengths. A magnetar is a reminder that even in death, a star's internal forces can remain almost unimaginably violent. A dying star can leave behind an object so dense that light cannot escape it. If the collapsing core of a massive star is heavy enough, not even the extreme pressure that supports a neutron star can stop the collapse. The result is a black hole, a region where gravity has become so strong that nothing, not light, not matter, not information as we understand it, can escape once it crosses a boundary called the event horizon. It is the most extreme ending available to a star, a final collapse with no known flaw. Black holes are not cosmic vacuum cleaners, they simply hold their old gravity. A common misconception imagines black holes actively pulling in everything nearby with overwhelming force. In reality, if the Sun were somehow replaced by a black hole of the same mass, Earth's orbit would barely change at all. The danger only appears at close range, near the event horizon itself. From a distance, a black hole behaves gravitationally just like the star that once occupied the same space, quiet and unremarkable until you get too close. Even black holes may very slowly fade away over time. According to an idea proposed by physicist Stephen Hawking, black holes are not perfectly eternal. Through an extremely slow quantum process now called Hawking radiation, a black hole can theoretically lose mass and energy over enormous timescales, far longer than the current age of the universe. For the black holes we know of today, this fading is so gradual it is essentially undetectable, but in principle, it suggests that even the densest, most extreme remnants of stellar death are not entirely permanent. Time itself behaves strangely near a collapsing star. As matter falls toward the extreme gravity of a forming black hole, time appears to slow down relative to an outside observer. From far away, an object approaching the event horizon would appear to move more and more slowly, seeming to freeze at the boundary rather than visibly crossing it. This bending of time is not an illusion of instruments. It is one of gravity's genuine effects, growing stranger the closer you approach a dying star's most extreme remnant. A star's explosion can send its leftover core flying through the galaxy. Supernova explosions are rarely perfectly symmetrical. Uneven ejection of material can give the resulting neutron star or black hole a powerful kick, sending it rocketing away from where it was born at speeds of hundreds of kilometers per second. These runaway objects can be found drifting far from any visible star-forming region, a quiet reminder that a violent birth can leave its remnant traveling alone through the galaxy for millions of years afterward. Two dead stars can slowly spiral toward each other for billions of years. When a supernova leaves behind a neutron star in a binary system, that neutron star and its companion, if it also becomes a neutron star, can continue orbiting one another. Over immense stretches of time, they lose energy through gravitational waves and drift closer together, orbiting faster and faster as the end approaches. This slow inward spiral can continue for billions of years before the two finally meet in one of the most dramatic collisions known to science. When two neutron stars collide, they can forge gold and platinum. This kind of collision, called a kilonova, releases enormous amounts of energy and produces conditions extreme enough to create some of the universe's heaviest elements. Gold, platinum, and other precious metals scattered across the cosmos are thought to have formed in exactly this kind of violent merger. In a very real sense, some of the jewelry worn on Earth may be made from material forged in the collision of two long-dead stars, flung outward long before our planet existed. Colliding neutron stars send ripples through the fabric of space itself. In 2017, astronomers detected gravitational waves from a neutron star merger, tiny distortions in space and time itself washing outward from the collision like ripples on a pond. For the first time, scientists were able to watch the same event in both light and gravitational waves, confirming decades of theory in a single, extraordinary night. It showed that the death of stars does not just release light and matter. It can shake the very structure of the universe. A single star's death can trigger the birth of new stars nearby. The shockwaves and enriched material released by a supernova can compress nearby clouds of gas and dust, encouraging them to collapse under their own gravity and ignite as new stars. In this way, a dying star does not simply vanish. It can act as a spark, seeding the next generation directly from the wreckage of the last, turning an ending into the opening chapter of something new. Almost every heavy element in your body was forged inside a dying star. Hydrogen and helium mostly trace back to the early universe itself, but nearly everything heavier, the calcium in bones, the iron in blood, the oxygen in every breath, was created through nuclear fusion inside stars and scattered outward when those stars died. In a very literal sense, the material that makes up a human body once belonged to stars that lived and ended long before the sun ever formed. Some stars die so quietly that no explosion ever happens at all. Not every ending is dramatic. Stars similar to the sun slip away through the slow, gentle sequence of red giant expansion, gas shedding, and white dwarf cooling, without any violent detonation at all. There is no flash, no shockwave, no burst of light visible across the galaxy, just a gradual, patient dimming that can unfold across hundreds of thousands of years, entirely without spectacle. The smallest stars in the universe may not have died even once yet. Red dwarfs, the most common type of star, burn their fuel so slowly and efficiently that their estimated lifespans stretch into the trillions of years, far longer than the current age of the universe itself. That means, as far as scientists can tell, not a single red dwarf has ever died of natural causes since the universe began. Somewhere out there, countless small stars are barely a fraction of the way through lives that will outlast almost everything else in existence. No white dwarf has ever had time to fully cool into darkness. A white dwarf slowly radiates away its remaining heat over an extraordinarily long timescale, theoretically fading eventually into a cold, dark object sometimes called a black dwarf. However, this cooling process is so slow that even the oldest white dwarfs in the universe have not yet had enough time to go fully dark. Every white dwarf we have ever observed is still, technically, glowing faintly, a fossil light that has not yet fully gone out. The very first stars in the universe may have died in an unusually extreme way. Long ago, before heavier elements had been created, the earliest stars were likely made almost entirely of hydrogen and helium. Some may have grown to enormous sizes, and models suggest a subset of them could have ended in an especially powerful kind of explosion called a parent stability supernova, in which the star is torn apart so completely that it leaves nothing behind at all, not even a neutron star or black hole. A parent stability supernova can obliterate a star entirely. In stars massive enough, extreme temperatures in the core can convert some energy into particle pairs, briefly reducing pressure support and causing partial collapse followed by a runaway explosion of fusion. Unlike an ordinary supernova, this process can be so complete and so violent that it destroys the entire star, leaving no compact remnant behind whatsoever. It is one of the rare stellar deaths where nothing solid remains, only expanding debris and an empty space where a star used to be. Some stars die twice, in a manner of speaking. Certain white dwarfs in binary systems undergo repeated smaller explosions called novae, brightening suddenly as fresh material from a companion ignites on their surface, then dimming again without being destroyed. Unlike a full supernova, the white dwarf survives each event, sometimes repeating the process again decades later. These recurring flare-ups are like small rehearsals of destruction, brightening and dimming a star that has not yet reached its true, final ending. A star can be stripped down to almost nothing before it finally explodes. Some extremely massive stars, called Wolf-Rayet stars, blow away their outer hydrogen layers through powerful stellar winds long before they die, exposing the hotter layers underneath. By the time such a star finally reaches its explosive ending, it may be almost unrecognizable from what it once was, a raw, stripped core of a star, burning fiercely and briefly before its final collapse. Some stars grow unstable and shed material in dramatic eruptions long before death. Massive, extremely luminous stars called luminous blue variables can experience sudden, violent outbursts, ejecting huge amounts of mass into space in relatively short bursts. The star Eta Carinii, one of the most massive and unstable stars known, experienced such an eruption in the 19th century, briefly becoming one of the brightest stars in the sky before fading, all while continuing to build toward an eventual, more final ending. The most extreme stellar deaths can create gamma-ray bursts visible across the universe. In certain massive star collapses, especially ones that produce rapidly spinning black holes, narrow jets of extremely high energy radiation can blast outward at nearly the speed of light. If one of these gamma-ray bursts happens to point toward Earth, it can be detected across billions of light-years, making it briefly one of the most energetic events observable anywhere in the cosmos, born from the final collapse of a single dying star. A dying star's light can reach Earth long after the star itself is gone. Because light takes time to travel across vast distances, many of the stars we see in the night sky are showing us light that left them hundreds, thousands, or even millions of years ago. Some of those stars may have already died, collapsed, or exploded in the time since that light began its journey. Looking up at the sky, in a very real sense, means looking at ghosts, glimmers of stars whose true, present fate we simply cannot yet know. Ancient civilizations recorded the deaths of stars without understanding what they were witnessing. In the year 1054, astronomers in China documented a brilliant new light in the sky bright enough to be visible in daylight for weeks. Centuries later, scientists identified the object at that location as the Crab Nebula, the expanding remnant of a supernova witnessed and carefully recorded by observers who had no concept of stellar collapse, yet still preserved a written record of the moment a star's death briefly lit up their sky. Some of history's most famous supernovae have their own names. Later observers such as Tycho Brahe and Johannes Kepler documented their own bright new stars appearing suddenly in the sky, in 1572 and 1604 respectively. Both are now understood to have been supernovae within our own galaxy, and both remain named after the astronomers who studied them carefully at the time, unaware they were witnessing the final, brilliant announcement of a star's destruction. A red supergiant nearing the end of its life sits relatively close to Earth. Betelgeuse, a massive red supergiant in the constellation Orion, is considered a strong candidate for a future supernova, though the exact timing remains completely uncertain and could be anywhere from tomorrow to hundreds of thousands of years away. When it finally does explode, it may be bright enough to be visible in daylight for weeks, a nearby reminder that the quiet stars overhead are not necessarily as stable as they appear. Some dying stars sculpt their own nebulae into strange, symmetrical shapes. Rather than expanding as a simple sphere, many planetary nebulae display intricate structures, rings, hourglass shapes, and delicate loops thought to be shaped by companion stars, magnetic fields, or uneven stellar winds. The Ring Nebula and the Helix Nebula are two well-known examples, each a glowing portrait of gas shed by a dying star, arranged into patterns that can look almost deliberately designed. The Helix Nebula has sometimes been nicknamed for its resemblance to an eye. Seen through powerful telescopes, this planetary nebula displays layered rings of glowing gas surrounding a small central white dwarf, giving it an appearance some observers compare to a great eye staring outward from deep space. It is, in truth, simply the outer atmosphere of a dying star, illuminated from within, drifting slowly outward in a shape that only looks purposeful by coincidence. A dying star can produce visible dust that eventually becomes part of new planets. As dying stars, especially in their red giant and supernova stages, shed material into space, some of it condenses into fine dust particles rich in elements like carbon and silicon. This dust drifts through interstellar space and can eventually become part of new molecular clouds, the very same raw material from which future stars and planets are built, threading a quiet line between one star's ending and another world's beginning. Some old stars orbited by planets may show their planets being slowly consumed. As a star swells into a red giant, Any close-orbiting planets may be gradually engulfed by its expanding outer layers, their material eventually mixing into the star's atmosphere. Astronomers have identified stars whose chemical composition suggests they may have consumed rocky material this way, meaning the death of a star can also, quietly, mean the death of any planets that once orbited too closely. A star's final composition can reveal how it died, long after the fact. By studying the chemical makeup of nebulae, supernova remnants, and surviving companion stars, astronomers can often work out what kind of star exploded, how massive it was, and even roughly how long ago the explosion occurred. In this way, a star's death leaves behind a chemical signature almost like a fingerprint, allowing scientists to reconstruct events that happened long before any human witnessed them. Neutrinos from a supernova pass through the Earth as if it were not there at all. During the earliest moments of a core collapse, the burst of neutrinos released is so penetrating that it passes not just through the dying star's outer layers, but straight through entire planets with almost no interaction at all. Detectors built deep underground exist specifically to catch the extremely rare occasions when one of these particles does interact, offering scientists a fleeting, precious glimpse of a star's death in progress. A supernova's shockwave can keep expanding for tens of thousands of years. After the initial explosion, the outward blast of material continues sweeping through interstellar gas, slowing gradually as it collides with surrounding material and sweeps it up like a snowplow. This expanding shell, known as a supernova remnant, can remain visible to telescopes for tens of thousands of years after the original explosion, a slowly fading echo of a moment that happened only once, briefly, long ago. Supernova remnants may be responsible for many of the high-energy particles striking Earth's atmosphere. Cosmic rays, extremely fast-moving particles that constantly bombard our planet from space, are thought to be accelerated in part by the shockwaves of ancient supernova remnants. In this way, the distant, silent death of a star long ago may still be quietly influencing the upper atmosphere above us tonight, in the form of tiny particles arriving from an explosion that ended long before recorded history began. A dying star can leave behind two completely different objects from a single explosion. In some supernova events, especially those in close binary systems, the explosion can eject one companion outward as a runaway star while transforming the exploding star itself into a neutron star or black hole. A single moment of death can therefore create two lasting consequences at once, a hurled survivor and a compact remnant, both permanently altered by an explosion that lasted only seconds. Neutron stars can have oceans and crusts unlike anything else in the universe. Some models suggest that a neutron star's outer layer may behave like an extremely rigid crystalline crust, while deeper layers behave more like an exotic superfluid, a state of matter that flows without friction. Beneath that may lie material so dense and strange that physicists are still uncertain exactly what state it takes. Even after death, a star's remnant can remain a genuine, active mystery. A magnetar's magnetic field could theoretically wipe a credit card from thousands of kilometers away. While no credit card has ever actually been tested that close to a magnetar, the physics is straightforward enough for the comparison to hold. Their magnetic fields are so extreme that they could, in principle, disrupt electronics, distort atomic structure, and interfere with delicate instruments from an almost unimaginable distance, one more reminder of just how strange the leftover remnants of dying stars can become. The death of a massive star can outshine everything else in its galaxy for weeks. During peak brightness, a supernova can briefly rival, or even surpass, the combined light of every other star in its host galaxy. From Earth, a supernova in a distant galaxy might appear as a single new point of light, easily mistaken at first glance for an ordinary nearby star, even though it may represent the final moment of an object that once dwarfed our own sun many times over. A dying star's outer shell can travel outward at thousands of kilometers per second. Material ejected during a supernova can reach speeds representing a meaningful fraction of the speed of light, tearing through space far faster than anything humans have ever built. This debris eventually slows as it plows into surrounding gas, but in its first years and centuries, a supernova remnant expands outward with a violence that is difficult to compare to almost anything else in the observable universe. Massive stars burn through their fuel far faster than smaller ones. Counterintuitively, larger stars do not necessarily live longer. They usually live dramatically shorter lives. A star many times the mass of the Sun may burn through its hydrogen in only a few million years, compared to the Sun's expected 10 billion year lifespan. The bigger and brighter a star burns, the faster it typically exhausts itself, meaning some of the most dazzling stars in the sky are also among the shortest lived. The most massive stars may collapse directly into a black hole without any visible explosion at all. In certain models, an extremely massive star's core collapse can proceed so completely and so quickly that the expected supernova explosion fails to fully develop, and the star seems to simply vanish from view, swallowed into a black hole without the expected burst of light. Astronomers have proposed a handful of candidate stars that appear to have disappeared this way, quietly, without the fanfare typically associated with stellar death. A star that vanishes without an explosion still leaves fingerprints behind. Even in a failed supernova, where a star seems to disappear directly into a black hole, its former presence can sometimes still be detected through its earlier gravitational influence on a companion star, or through a faint burst of infrared light released just before it vanished. The universe rarely erases evidence completely, even in its stranger, quieter deaths. Binary star systems can share mass so intimately that both stars lose their original identity. In extremely close binary systems, physical contact and shared outer envelopes can blur the boundary between two individual stars, a phase sometimes called common envelope evolution. This process can dramatically reshape both stars' eventual endings, sometimes causing one to shed its outer layers early, sometimes drawing the pair into an eventual merger, tangled together until their fates are no longer separable. Two white dwarfs can merge and reignite as a supernova of their own. If two white dwarfs in a binary system spiral together and finally merge, their combined mass may exceed the Chandrasekhar limit, triggering a runaway explosion similar to the more familiar mass transfer version of a Type Ia supernova. In this case, it is not one star stealing from another, but two stellar remnants slowly dancing closer over billions of years before combining in one final, decisive burst of light. Some supernovae leave behind pulsars spinning at astonishing, almost musical rates. The Crab pulsar, remnant of the supernova recorded in 1054, spins roughly 30 times every second, sweeping its beam of radiation past Earth with metronomic regularity. Scientists have even converted these signals into audible tones, allowing a listener to hear, in a sense, the steady pulse of a star that finished dying nearly 1,000 years ago, still ticking quietly in the dark. Some dying stars have companions who never even notice the loss. In wide binary systems, where two stars orbit each other at a great distance, one star can go through its entire death, expansion, explosion, and collapse, without dramatically affecting its distant partner at all. The surviving star may simply continue its own life relatively undisturbed, orbiting a faint remnant, or in some cases an entirely invisible black hole, for the rest of its own long existence. A star's final gasp of fusion can happen only hours before its explosion. In the last day of a massive star's life, its core fuses silicon into iron with startling speed, a process that might take mere hours compared to the millions of years spent earlier fusing hydrogen and helium. This final acceleration reflects how unstable and rushed the last chapter of a massive star's life truly becomes, the calm of earlier eons giving way to a frantic final countdown. An iron core cannot be fused into anything more without costing the star energy. Iron sits at a special point in nuclear physics where fusing it further requires more energy than it releases. Once a massive star's core becomes mostly iron, fusion effectively stops paying its own way, and without that outward energy, the core has nothing left to resist gravity. This single fact of nuclear physics is, in a very real sense, the reason massive stars are ultimately doomed to collapse. The core of a collapsing star can undergo a process called photodisintegration in its final instance. As temperatures soar during collapse, high-energy photons can begin breaking iron nuclei back apart into smaller particles, a process that absorbs even more energy and accelerates the collapse further. It is a strange, self-feeding spiral, the star's own extreme conditions actively working against its remaining structure in the final fractions of a second before total collapse. Some stellar remnants remain gravitationally bound to the planets that once orbited their parent star. When a star becomes a white dwarf, any distant planets that survive the earlier expansion phase can continue orbiting the shrunken remnant indefinitely. Evidence of shattered asteroids and disrupted planetary material has been found swirling around some white dwarfs, suggesting entire miniature planetary systems can persist, quietly circling the compact leftover core of the star that once warmed them. The universe is expected to enter an era where star formation eventually stops entirely. Astronomers refer to the current period as the stelliferous era, a cosmic age defined by widespread star formation and shining stars. Over trillions of years, the raw gas needed to form new stars will gradually be used up, and eventually, existing stars will finish dying without replacement. Long after that, the universe is expected to become a much darker, quieter place, populated mostly by cold remnants rather than bright, living stars. The very last stars to shine may be extremely faint red dwarfs. Because red dwarfs burn their fuel so slowly, models suggest they could remain the last actively fusing stars in the universe, continuing to glow dimly long after every larger star has already died. Even they, eventually, will exhaust their resources, cooling gradually into dark remnants over spans of time so long they are difficult to meaningfully compare to anything in ordinary experience. A black dwarf, the final theoretical stage of a white dwarf, has never actually been observed. Because white dwarfs cool so slowly, and because the universe is not yet old enough for any of them to have finished that process, black dwarfs remain a purely theoretical endpoint. If the universe continues long enough, existing white dwarfs are expected to eventually fade into cold, dark spheres of degenerate matter, radiating no visible light at all, silent remnants of stars that finished their story long, long ago. A single meadow-sized patch of the night sky can contain the light of stars in every stage of dying. Look up at almost any clear patch of night sky, and you are seeing stars in vastly different chapters of their lives at once, some still steadily burning hydrogen, some swelling into red giants, some quietly cooling as white dwarfs, and perhaps one or two, unknown to us, in the final hours before an explosion no one has yet witnessed. The sky is not a single, static picture. It is a vast, layered gallery of endings unfolding at different speeds. Some supernova remnants form beautiful, filament-like structures that persist for millennia. Long after the initial explosion, the expanding, cooling gas of a supernova remnant can settle into delicate, thread-like filaments, glowing softly from the leftover energy of the original blast. The Veil Nebula, remnant of an ancient supernova, displays exactly this kind of intricate structure, a quiet, glowing lattice spread across a portion of sky, slowly dispersing into the surrounding interstellar medium over tens of thousands of years. Modern space telescopes have revealed extraordinary new detail in the remnants of dead stars. Instruments capable of observing in infrared light have captured intricate structures within supernova remnants and planetary nebulae that were previously invisible, layers of dust, delicate shells of gas, and subtle patterns shaped by the star's final years. Each new image adds detail to a story that began with a single star's ending, sometimes thousands of years ago, still slowly unfolding in the quiet dark. A star that dies in isolation can leave behind an object with no witnesses at all. Not every dying star is fortunate enough to be observed. Countless stars throughout the galaxy's history have surely ended their lives unnoticed by any observer, their explosions and collapses occurring in obscured or distant regions, their light absorbed by intervening dust, or simply happening long before any species capable of watching existed at all. Most of the universe's stellar deaths have gone, and will go, entirely unseen. Stellar death is, in some sense, the universe's method of recycling itself. Every dying star returns material to the surrounding galaxy, gas, dust, and heavier elements that eventually become part of new stars, new planetary systems, and potentially new life. Rather than representing a true ending, a star's death functions more like a transformation, one chapter closing so that the raw material can be gathered again into something new, somewhere else, sometime later. Some of the calcium in your bones was forged specifically inside a massive, exploding star. While lighter elements can form in ordinary stellar fusion, calcium, and many other elements essential to biology require the extreme conditions found only during a supernova. In a very literal sense, part of your own skeleton was created inside the final, violent moments of a star's death, long before the sun, the earth, or any living thing existed at all. The iron in a single drop of blood may have come from more than one dying star. Because interstellar material mixes and disperses over such long timescales, the elements found in any small sample of matter, including the iron carried in blood, likely originated from multiple separate stars that lived and died at different times, in different parts of the galaxy, long before combining together in the cloud of gas and dust that eventually formed the solar system. Some scientists describe humans, quite literally, as a kind of stardust. This is not simply poetic language. Every atom heavier than hydrogen and helium in your body was forged either in the heart of an ordinary star or in the extreme conditions of a star's violent ending. When you consider the calcium, carbon, oxygen, and iron that make up a living body, you are looking at material that was quite literally cooked inside stars that finished their lives long before our solar system ever began to form. A star's death can determine the very shape of the galaxy it leaves behind. Repeated supernova explosions across a galaxy's history contribute to shaping its structure, stirring gas, triggering new star formation, and distributing heavy elements throughout its spiral arms or central regions. Over billions of years, the cumulative effect of countless individual stellar deaths can influence how an entire galaxy looks and evolves, an enormous structure quietly shaped by the endings of its smallest, most numerous residents. Even the darkest regions of space carry the leftover heat of ancient stellar deaths. Cooling white dwarfs, fading neutron stars, and slowly evaporating black holes continue to radiate faint traces of energy long after their dramatic endings have passed. Even in the coldest, quietest corners of the universe, the leftover warmth of long-dead stars lingers, fading gradually across timescales that dwarf the entire recorded history of humanity many times over. A star's ending can sometimes be seen twice, thanks to gravitational lensing. In rare cases, the gravity of a massive galaxy positioned between Earth and a distant supernova can bend and split the light from that explosion into multiple separate images, arriving at slightly different times. Astronomers have observed the same supernova appear to flare more than once in different parts of the sky, a strange gravitational echo allowing a single stellar death to be witnessed more than once. Some ancient supernova remnants are only detectable through the radiation they still emit. Long after visible light from an explosion has faded entirely, the remnant may still emit radio waves, X-rays, or other forms of radiation detectable only with specialized instruments. This means some of the oldest recorded stellar deaths remain, in a sense, still faintly glowing, if you know which invisible wavelength of light to look for. A star's death can trigger chain reactions across an entire star cluster. In densely packed young star clusters, a single massive star supernova can compress and disturb the surrounding gas so significantly that it triggers the formation of several new stars in quick succession. In some cases, this can even set off additional deaths, as later, newly triggered massive stars burn through their own short lives and explode in turn, one ending prompting several new beginnings and eventually more ending still. Astronomers can sometimes predict a star's coming death years in advance. By studying a massive star's brightness, temperature changes, and internal instability, astronomers can occasionally identify strong candidates likely to explode as supernovae relatively soon, at least on astronomical timescales. Precise timing remains extremely difficult to pin down, but the ability to flag a star as nearing its end shows how deeply we have come to understand what a dying star's final years actually look like. A dying star's brightness can briefly resemble a heartbeat before its final collapse. In the days or weeks before some supernovae, subtle pulsations or brightness variations have been observed, suggesting the star's internal structure is becoming unstable in its final approach to collapse. These faint fluctuations, largely invisible without careful monitoring, represent one of the few advance warnings nature offers before a star's sudden, dramatic ending. The death of a star can be witnessed from almost unimaginable distances. Because supernovae are so extraordinarily bright, telescopes can detect them in galaxies billions of light-years away, meaning the explosions being observed actually occurred billions of years in the past, long before the Earth itself existed. Watching a distant supernova is, quite literally, watching backward through cosmic time to witness the death of a star from an era before our own planet had even formed. A star's remnant can become the seed around which an entire new star system slowly forms. In some cases, leftover gas and dust surrounding a stellar remnant can eventually gather and collapse to form a fresh accretion disk, occasionally giving rise to new planets or smaller companion objects. Even after a star's core has finished its explosive transformation, the debris field left behind can, given enough time, become the quiet beginning of an entirely different kind of system. Stellar death teaches us that endings and beginnings are rarely fully separate events. Across the long history of the universe, dying stars have provided both the raw material and the triggering force behind countless new stars, planets, and possibly the chemistry necessary for life itself. What looks, from a distance, like destruction is very often also construction, gas and dust rearranged rather than erased, patiently gathering itself once again into something new. As our journey through the quiet death of stars comes to a close, perhaps the sky above feels a little different now. Not simply a scattering of fixed points of light, but a vast, slow theater of endings, some gentle, some sudden, some so quiet they may never be witnessed at all. We've drifted through swelling red giants and fading white dwarfs, through the violent instant of core collapse and the silent stretch of a neutron star spin, past Kilonovae forging gold in the dark and dust clouds slowly gathering into the beginnings of something new. Every dying star we've wandered past tonight has, in some small way, helped build the very atoms resting quietly inside you right now. Now you can let all of that drift softly into the background. Let your breathing slow. Let your shoulders loosen. Let the images fade from bright detail into something softer and more distant, like the last fading glow of a white dwarf's light, dimming gently into the endless quiet dark. And if you enjoyed this journey, perhaps you might like, subscribe, or share a thought below. It helps other curious minds find their way here, too, one quiet universe at a time. And if you happen to still be awake, there will be another slow journey waiting for you on the screen, another quiet corner of the cosmos to drift into gently. But for now, let your mind grow still, and let the day fall away. Sleep well, and good night.